solution. Also, UP is
This meeting is being recorded.
Also, UP is non-degenerate. So now we can give the scaling of UP as the following. Then we can use the unique positive solution of this problem to construct the unique positive solution of this problem with the mass lambda. Okay. Then we can compute the mass of the unique positive solution U lambda p. We can find that the L2 norm of U lambda p equal to lambda to power 4 minus p minus 2 times n over 2 times p minus 2 times the mass of UP. From this quantity, we know if this exponent is positive, we can show that as lambda goes to 0, the mass of U lambda p goes to 0. If lambda goes to plus infinity, we know the mass of U lambda p goes to plus infinity. Also, we can consider the negative case. For example, if this exponent is negative, we also can choose the similar behaviors. Okay. So now we can give the picture of the mass of U lambda p. So from this picture, we know the behavior is different from p. Different if p lies in different integral. For example, if p is greater than this exponent, we know the picture. The picture is like this. Okay, so if p is less than exponent, we know the mass of U lambda p behaviors like this. Okay, so we know for this case and for this case, for any a, we know this line has only one intersection with this curve. Okay. For the last case, if p equal to this exponent, we know this line can intersect. This line can intersect the mass of U lambda p if and only if the constant a equal to the mass of UP. Okay. So here we know the exponent, this exponent 2 plus 4 over n is critical. Okay, this means that if p is different from p bar, we know there is a unique lambda a such that the mass of U lambda p equal to a. Okay, but if a is equal to p bar, we know the problem 1 has a positive normalized solution if and only if a is nothing but the mass of UP. Also, for this case, we know the problem 1 has infinitely many solutions with the mass a. Okay, so we call this exponent is called mass critical exponent. So if p is less than this exponent, we call this case mass subcritical case. If p is greater than this exponent, we call this is mass supercritical exponent, supercritical case. Okay. So in the literature, people consider the normalized problem in mass subcritical case, critical case, and mass supercritical case separately. So usually people can use a variational argument to find a normalized solution, but the methods are different. Okay. So now we give the following remark. So for the problem 1, we know this nonlinearity is homogeneous. So we can use the scaling argument to construct the normalized solution of this problem. Okay. So if we consider the non-homogeneous nonlinearity G of S, such scaling argument is not valid anymore. So people can use variational argument to find normalized solution. So usually people can consider the following constraint problem subject to the constraint sphere S of SA. Okay. So usually people can choose the minimizer of G of U over this sphere, and people can choose that the minimizer can be achieved and satisfy some problem with one unknown parameter. Usually here, the parameter lambda appears as a Lagrangian multiplier and is not a previous known. Okay. So if people want to find some minimizer G of U over this sphere, people have to consider the mass subcritical, mass critical, mass supercritical separately. Okay, because for the mass subcritical case, we know the energy function G of U is bounded from below on sphere SA for any A positive. For mass supercritical case, the energy function G of U is unbounded from below for any A positive. For the mass critical case, the boundedness from below depends on the value of A. So we know for the first case, people can find global minimizers of G of U over the sphere SA. But for the mass subcritical case, it's impossible to find the minimizer of G of U over the sphere SA. So the different for the subcritical or supercritical are completely different. So in the following, we mention the following reference for the related results. For example, Strode first considered the mass subcritical case, and he proved the extent of normalized solution in the mass subcritical case. Recently, Zhang and Lu considered the normalized solution, but the solution can be non-reduced. Also, Shibata can prove the extent of global minimizers. Okay. So also, Zhang, Bach, and Solvi, Ikma, Tanaka, and Solvi consider the mass supercritical case. Okay, compared to mass supercritical case, we know the energy function G is unbounded from below over the sphere SA. So they considered some local minimizer of function G of U on some subside of sphere SA. Actually, Zhang found a new argument to find some mountain path geometry on SA, then he can prove that there is a bounded Pálmar sequence on the sphere SA. Then he proved the existence of a normalized solution in the supercritical case. Okay. Also, Jeanjean and Lu consider the existence of sign-changing normalized solution. Okay. Also, people consider the normalized solution in the subcritical case. This means that they consider the problem involving subcritical exponent. Okay, so the main difficulty lies in the compactness. So people use some argument trying to recover the compactness. Okay, so in this paper, Juncheng Wei and Wu solved one problem which suggested by Zhang. Because in this paper they just consider the case, just consider the higher dimensional case. Actually, they consider the 4 and 5 dimensional case. In this paper, the 3-dimensional case is also considered. In this paper, Professor Zhang and Luo then considered a fractional case for the normalized solution. Okay, also Professor Guo and GQ Wang and Professor Peng, they also consider the mass concentration problem. Okay. Okay, now we give the main purpose of my talk. In this talk, our aim is to present a different approach. Okay, so our approach is mainly based on the fixed point index and continuation arguments to study the normalized solution. Also, our approach does not rely on the variational structure. This means that we can also consider the problem with the non-variational structure, and we can treat subcritical, mass critical, and mass supercritical case uniformly. Okay. Also, our approach is different from the fabrication methods. So here, in our work, we does not in our paper the well-known Ramanujan global fabrication argument seems not valid for our problem. Okay, because usually fabrication argument depends on the eigenvalue. Okay. So now we introduce a very related work due to Thomas Bach, Wenming Zhou, and Zhong. In this work, they consider the following Bose-Einstein system. Also, they use the global branch argument to find the existence of a normalized solution. Okay, so our work is closely related to this paper, but our problem is different also. In this work, the nonlinearity is homogeneous, but in our work, the nonlinearity is non-homogeneous. Okay. So now we give the main hypothesis of my work. First, we assume G is positive and it's of C1 class. Also, it assumes the following assumption on G. Actually, we should know the behavior of G near origin and infinity. Also, it assumes G3. This assumption assumption is used to get some Liouville type theorem. Okay. So now we give the remark for the last assumption. Okay. Usually, G3 is only required for the higher dimensional case. Also, with alpha minus 1 is directly bigger than n over n plus 2. So this means that if n equal to 1 and 2, G3 is always true. Also, if alpha minus 1 is less than n over 2 minus 2, G3 also is true. Okay. So here we just want to use this G3 to get some Liouville time theorem. Then we can use this Liouville time theorem to get some contradiction. Okay. In particular, for the case of n greater than 3, with alpha minus 1 is directly bigger than n over 2 minus 1. So we can show that the last assumption G3 can be deduced from this assumption. So we can give a very popular prototype. For example, G of S equal to S to the power P. So if P is less than the exponent to star, G3 is true. Okay. So here we can give one open question. So for the case of n bigger than 3 with alpha minus 1 is directly bigger than n over 2n minus 2, whether G1 and G2 can give the assumption S times G of S is less than 2 star times G of S. Okay. So if so, we can remove our last assumption G3. But actually now we cannot prove this. So now we show our main results. So we prove that if n is bigger than 1 and assume that G1, G2, and G3 hold, then we can prove that the following results. So first, in the mass subcritical case, if alpha beta is between 2 and the critical exponent, we can show that for any given A positive, our problem always has a positive normalized solution. Okay. So this means that the normalized solution exists globally. Okay. Because here we do not give any restriction on the mass A. Okay. So here we can give the picture of the mass. Okay. For any mass A, we can find a normalized solution with the mass A. Okay. But we do not know the normalized solution is unique or not. Okay. So now we consider the mass critical case. So if alpha equal to beta equal to the critical exponent, this means that our problem is mass critical both in the origin and infinity. So we can find some constant. We can find some constant, this positive constant and this positive constant, and shows that our problem has a normalized solution if the mass A is between this constant and between this constant. Also, we can show that if the mass is very small or large enough, the problem 1 has no positive normalized solutions. But we do not know this problem. We don't know if this problem has some changing normalized solution in the range of A. Okay. Okay. So here we show that in the multiplicity case, the problem does not always has normalized solution. So the distance depends on the range of A. Okay. So now we consider the at most the multiplicity case. So if the problem is subcritical near origin and critical near the infinity, we can show that our problem has at least one positive solution if the mass is small enough. Okay. Also, we can show that if the mass is large enough, the problem has no positive normalized solution. Okay. So from these results, we can find that the behavior of the nonlinearity G near origin and infinity can decide the distance and non-extents of normalized solution. Okay. So for this case, the problem is subcritical near infinity and critical near origin. We can show that the problem has a normalized solution if the mass is large enough and the problem has no positive normalized solution if the mass is small enough. Okay. So now we consider the mixed cases. If the problem is mass subcritical near origin and mass supercritical near infinity, we can find two positive constants A star and M. Actually, we show that the problem has at least two different positive normalized solutions if A is small, and the problem has no positive normalized solution if A is large enough. Okay, this case is similar. Okay, so for the problem, so if the exponent satisfies this assumption, that is the problem is mass subcritical near infinity and mass supercritical near origin, we can find the similar results. Okay. Okay. So now we consider at least the mass critical case. So if the problem is mass critical near origin and mass supercritical near infinity, we can show that the problem has at least one positive normalized solution if the mass is small enough, and the problem has no positive normalized solution if the mass large enough. Okay. Also, for this case, we can get the similar results. Okay. For this case, the problem is mass supercritical near origin and mass critical near infinity. We also find extents and non-extents of normalized solution depending on the mass A. Okay. Okay. So now we consider the mass supercritical case. If the problem is supercritical, is mass supercritical near origin and infinity, we show that the problem has a normalized solution for any A. So in this case, it's very similar to the mass subcritical case. So for the mass supercritical case and mass subcritical case, we show that this problem has always have positive normalized solution for any positive A. Okay. Okay, so this is the main result of my talk. So in the following, I will give the proof. Okay. So our proof mainly depends on the following steps. So first, we show to show the existence of a continuum of positive solution. Usually, we should understand the behavior of the L2 norm of positive solution as lambda goes to 0 or lambda goes to plus infinity. Okay, so here we point out that our argument highly depends on the behavior of the nonlinear G near origin and infinity. So this means that the behavior of G near origin and infinity can guarantee the existence or non-existence of nominal solution. Okay. So now we give the following results for the behavior of the L2 norm of positive solution. So using this result, we can show that as the lambda goes to plus infinity, we can show that the L infinity norm of UN goes to 0, and the mass of the solution, goes to 0 in the mass supercritical. The affinity is the norm. Affinity is the norm of the unique positive solution of the limit problem in the mass critical case. And for the supercritical case, we show that the mass of UN goes to plus infinity. Okay, so from this result, we know the mass of the solution UN has a different behavior in the mass subcritical, mass critical, and mass supercritical case. Okay. Okay. Also, we can find the similar behavior of the L2 norms of positive solution. Okay, in H1. Okay, so this result is similar. To this result. Okay, in this part, we show the behavior of the solution as lambda goes to 0. In this result, we show the similar behavior of the solution as lambda goes to plus infinity. Okay. Okay, so from the result, we also know the behavior of the nonlinear G near infinity can show different behavior of the mass of UN. Okay. Okay. So our basic idea is that first we want to show some behavior bonds on the L2 norm of positive solution. Then we can prove the compactness of the set of positive solution, both in the sense of CR0 and in the sense of H1Rn. Okay. Then we can use the blow-up argument to show the behavior of the positive solution both in CR0 and in H1 in H1Rn as lambda goes to 0 or lambda goes to plus infinity. Okay. Finally, we can show that the uniqueness of positive solution of the problem 1 for lambda positive small or large. Okay. So usually to get the uniqueness of the positive solution, we just need to know the behavior of the nonlinear G near 0 or infinity. Okay. Okay. So for the one-dimensional case, we know the problem always has normalized solution for every lambda. Also, we know the set of possible solutions is connected. Okay. So the one dimensional case is simpler. But for n is bigger than 2, the problem is a little bit complicated. To get the normalized solution of higher dimensional case, we need to know the situation near the origin. Actually, we can choose that for n is bigger than 2. We can use the uniqueness of normalized solution of the problem near origin. We can choose that the curve. We can choose that the side of a solution for lambda small light one curve. Actually, we choose that the side of lambda u lambda is just the curve for lambda positive small. Okay. Also, for n is directly is bigger than 2. If we denote by s, the side of solution of the normalized solution problem, we just need to choose that if this side has a unbounded component astute, more precisely letting the projection P1, okay, P1 from this space to this integral. And if we want to show for any lambda, the problem has a normalized solution. We just need to prove that the range of P1 is the interval from 0 to plus infinity. Okay, so to show this, we will use topological degree argument combining with local index. Okay. Okay. So to show this, first we show that the normalized solution. For lambda solution, we just need to consider the case of lambda is directly positive, because for lambda is negative, we can choose that the normalized solution 1 has no non-trivial, non-negative classical solution. Okay, so here we usually can use Pós-graduação angle argument to show this non-extensive results. Also, we can show that for the zero mass case, the problem has no non-trivial solutions. Actually, we choose the following result. Okay, so this is why we just consider the case of lambda is lambda positive. Okay. So okay, now we already know the extent of normalized solution for lambda small and for lambda large. So we just know what happened between large lambda and small lambda. So for this case, we just define the set of solutions with the parameter lambda bounded. So actually, we can show that this side is compact in the space CR0 and H1. Also, we can show that this side is uniformly bounded from above. Okay. So using this a priori estimate, we can use the topological argument to show that there's a unbounded continuum in the solution side S. Okay. To do this, we also need the following asymptotic behavior as lambda goes to 0 or lambda goes to plus infinity. Okay. So we choose that as lambda goes to 0, actually we show that the solution, normalized solution UN will goes to 0 in the L infinity norm. Okay, so we know if lambda goes to 0, using some scaling argument, we can show that the problem can be reduced to some limit problem. Also, we know the limit problem heavily depends on the behavior of G near origin. So to understand where the normalized solution, we just need to understand where the limit problem. Okay, actually we know the limit problem has a unique and non-degenerate positive solution. Okay. Also, we know the following behavior of the solution. Okay, as lambda goes 0. Okay. Okay. Also, we know the similar result in the sense of H1. It's H1, the space H1. Okay. The result is very similar, but we just consider the similar problem in the different space. Okay. Also, we also need to understand where the problem near infinity. Actually, we show that as lambda goes to plus infinity, we show that the R infinity norm of UN goes to plus infinity. So with the similar scaling argument, we can show that the problem can be reduced to the limit problem at infinity. So the limit problem relies on the behavior of the linear G near infinity. Okay, so from these results, we know the limit problems of our problem at 0 or infinity can give the existence or non-existence of nominal solution. Okay. Also, this similar result as lambda goes to plus infinity in CR0 space and H1 are in space. Okay, because the result is similar, so we do not give the proof. Okay. Okay, the following result is shows that the uniqueness of the problem near origin and or infinity. Okay. So okay, just like what I mentioned a few moments ago, we know first we show the extent of nominal solution near origin and or near infinity. Okay, so actually we know if lambda is small or lambda large enough, we can show that the problem 1 has a nominal solution. Also, the nominal solution, the positive nominal solution is unique. Okay. Also, we know for lambda large or lambda small, actually for lambda small, we can show that the positive solution lies one curve. Okay. Okay. Also, for the higher dimensional case, we can show the similar result. Also, we show that the curve is continuous. Also, the curve shows that the uniqueness of normalized solution for lambda small. Okay, but here we point out that usually for the scalar field problem, the uniqueness of positive solution is still open, because in this paper, Davila, Del Pino, and Guerra prove that the scalar field problem with this nonlinearity has at least 3 different positive solutions. So for so in general, for the scalar field equation, the possible solutions are not unique. Okay. So in our work, actually we can show that if the mass lambda is very small, for the general nonlinearity G, the possible solution is unique. In this paper, the mass lambda is fixed. Okay. So if lambda is very small, we can choose that the possible solution should be unique. Okay. Okay. So now this case is so this result is about the one-dimensional case. Okay. Also the curve, which we can choose that for any lambda, because particulars also Jeanjean Tanaka already shows that for any lambda positive, the problem 1 has a unique possible solution. Also, the set of possible solution is connected and it's the curve. Okay, so for the one-dimensional case, you already known. Okay. Okay. So now we consider the case of n greater than 2. So under the assumption G1, G3, we can show that the local curve above belongs to a connected component of a set of possible solution. Also, this component contains a possible solution for every lambda. Okay, for every lambda. To show that, we will use some topological degree argument. Actually, we consider the following operator, the gradient of G lambda, and we can use the classical degree theory for this operator. So this means that the fixed point of this operator, so any fixed point of this operator is just the one solution of the original problem. Okay. So actually, we will use the local fixed point index, because we already know the operator T lambda is completely continuous. Also, we know for lambda small is very small, the possible solution of the original problem is unique. So for lambda very small, we know the local fixed point index is well defined, because if we want to give the definition of the local index, we should know the fixed point is isolated or not, because here for lambda very small, the possible solution of the original problem is unique. So we know the local fixed point index is well defined. Okay. Also, we can show that for lambda very small, the local index of U lambda is just -1. Okay. Also, we show that for lambda is bounded from below or from above. We can show that the problem is the problem. We know for lambda bounded from below or above, the possible solution is uniformly bounded. So we can use the topological argument to show that for any lambda, the T lambda always has the fixed point. Then we can show that our problem has a normalized solution for any lambda. Okay, so actually we can show that the range of P1 is the integral from 0 to plus infinity. Okay. Okay, in the following, we can use our argument to show our main results. Okay, actually, we just need to know the behavior of the mass near zero or plus infinity. Okay, so maybe my time is over. So I just give the main proof of the first one. Okay, so for example, for the 1 and 2 dimensional case, we know the range of P1 is the positive part of lambda axis. So this means that there is a solution belong to asymptotic for lambda very small. The mass of un goes to 0. Okay. So similarly, for lambda goes to plus infinity, we know the mass of u goes to plus infinity. Okay. So since the side of asymptotic is connected, so we show that the range of rho is the positive part of x-axis. Okay. Okay. So for the following proof, I think maybe my time is over. So I just sketch them. Okay. Okay. So many thanks for your attention.
Thank you, Professor Zhang. Any questions? No questions? I have a question, Professor.
Okay.
What happens when P is bigger than 2 star?
Okay. So if the P is bigger than 2 star, maybe the problem is very difficult because we know if P is bigger than 2 star, we could not consider problem in the sublevel space H1. Because our argument highly depend on the limit problem. The limit problem. Okay, because okay, this one. This one. Yeah, this one.
Yeah.
So actually, we shouldn't know. So we shouldn't know this limit problem has a unique and non-degenerate positive reduced solution. So if P is bigger than 2 star, so we do not know the positive solution of this problem is unique or non-degenerate.
Okay.
Yeah, because maybe the L2 norm of the UP maybe is finite for P is bigger than 2 star.
It maybe needs one parameter. This case.
This case, right? This case, that's one.
Yeah, when P is bigger than 2 star, maybe need a parameter the front of the nonlinear term.
Also, in our work, we could not consider the case for P critical. So if P is equal to 2 star, we also could not consider this case. Because if P is the critical, we do not know this problem has positive solution or not. Actually, we know no, because if P is to 2 star, the problem has no non-trivial solution for lambda positive. So in our work, we can just consider the case of P belonging this range.
Okay, thank you. Any more questions? No questions. Thank you very much, Professor Zhang.
Thank you. Obrigado.
这个地方那个有人好像留言了啊，我看看，你看得到吗？
有点。
看到。
好的。The solution has finite energy and of class H1. So yeah. Yes. Many thanks for your suggestion. Yes. Yes. Your remark is very good. Yes.
Okay.
Also in Italy, I also discussed the supercritical case with Thomas Bach. Also, he thinks that the supercritical case seems very difficult because we do not know how can we consider this problem in variational framework. Yeah.
那好吧，那谢谢张老师啊，一共
哎呀，太客气。这个好久没有练了，我有点紧张，好久没有练了。